In the last couple of videos, we've been taking a look at the impulse momentum theorem and momentum conservation. And this seems like a good segue to get into discussing conserved quantities in general. When a physicist says that something is conserved, what they mean by that is that the quantity remains constant throughout a process. So just to make that a little more concrete, let's say that we have Joe and Jane, and Joe is going to buy a collectible object off of Jane for $10. What we could do is we can look at the process. And what we can do is we can look at the amount of money in each of their wallets. So before the transaction, with Joe buying the collectible figure, Joe had $20 in their wallet, and Jane had, $30 in their wallet. And after the transaction, Joe's wallet is $10 lighter, and Jane's wallet is $10 heavier. If we add up all the money in both wallets, we see that both before and afterwards, there was $50 across both wallets. So if we were to use physics jargon to describe what is happening here, we would say that the amount of money in wallets is conserved under exchange of collectible figurines. So that may be a little bit of a contrived example, but there are examples of such quote-unquote natural money in physics. And we've already seen one with the case of momentum conservation. And we've already seen that we can exploit the fact that the quantity is conserved to get a variable we want without having to do more tedious calculation. So here I'd like to introduce another kind of natural money, if you will, another quantity that physicists find is conserved in across interactions as long as you do adequately careful bookkeeping. And that quantity is energy. Broadly, we can break kinetic energy into two kinds, and then we can get into subcategories and will. One variety is kinetic energy. And this is associated with the motion of an object, specifically its speed. The faster something goes, the greater the kinetic energy. And this quantity is always positive. Then there's potential energy. And we will get into why it's called potential later. This one's a little fussier. It's associated with the relative position of two objects and the conservative force by which they are interacting. So this can be positive or negative. And can often depend on choice of coordinates. However, regardless of the choice of coordinates, delta U is always the same for a process. So there we go. Now I did use, without defining, the term conservative force right here. And we'll hold off on doing a formal definition of conservative force for a bit. For now, we can just say no friction, no air resistance, that kind of thing. But we'll do a more rigorous formal definition in a bit. Okay, so things that we will show, but for now I will just give as examples. The kinetic energy of an object will turn out to be 1/2 the mass of the object times the square of its speed. So this is a scalar quantity. All energies are scalars. So they're just numbers. This is different than momentum. Momentum is vectors, and we have to keep track of x, y, and z coordinates separately, components separately, and we have to keep track of our plus and minus signs for direction. With energy, energies are always just numbers, and you can kinetic energy, it will always be a positive number. Potential energies could be positive or negative, but again, they're just numbers. And sorry, I wrote delta U there, and I should have been writing delta PE. And as an example here, you can look at the potential energy associated with gravity near the surface of the Earth. We'll show that this is equal to the mass of the thing times the gravitational field strength G times the y coordinate of the thing. So different choices of y coordinates of where you want to put y equals 0 will yield different values for potential energy, but we'll see that that usually doesn't matter. That all matters the changes in values, and the changes will be the same regardless of where you choose 0 to be. So if we play with either of these quantities here, we'll see that they both have units of kilogram meter squared per second squared. And this combination shows up so much that it gets its own special name. It's called the joule, Joule. It's after the person who demonstrated that that heat flows could be understood as transfers of internal energy. More on that when we get to the unit on thermodynamics. So where we'll be going with this is that if our system is conservative, and again, I have not formally defined conservative yet, we'll just take that to mean no friction. The total mechanical energy, which is defined to be the sum of the kinetic energy plus the potential energy, is a constant. So we can write this as the energy at the end of the process, E final, is equal to the energy at the beginning of the process, E initial. So like I say, for the moment, we'll take conservative system to mean no friction. They'll also turn out, and we'll prove this shortly, that there are forces that are always acting perpendicular to the motion, like for instance the normal force of a surface on something sliding along the surface. We'll also be able to ignore any of those forces as well. So we'll prove that in a bit. But the nice thing about it here is that, let's say you're riding down a roller coaster or something like that. So here you are. Sorry, I've never been able to put my hands up. I'm a loser. So up here, you're basically not moving. So we'll say your speed is 0. So if we were to kind of just make a sort of like a bar chart here. Whoops. Try that again. Here to try to make a bar chart here. All the energy that we would have would be potential. You're at your highest point up, so your y coordinate is the biggest, your energy is the highest. Now when we get, say, down to this point right here, here your potential energy has dropped to 0, but if we take a look at your kinetic energy, we'll see that the kinetic energy is equal to the potential you had before. And let's say you're at some intermediate point here, like on the top of this loop-de-loop here. Again, I can make a bar representing my total mechanical energy. And what I'll see is, okay, my height has increased, so I've increased my separation between the Earth and me. So that's increased my potential energy. And what we find is that my kinetic energy has to decrease to match. So, but assuming no friction, the total amount of energy, the height of this bar, stays the same the whole time. We just shift back and forth between forms. So if we can figure out what one of the values is, what one of the values of one of the kinds of energies is, we can get the other one, and from that figure out a speed or a height or whatever it is that we require. Now, I've been mentioning friction quite a bit. And I think you know from practical experience that when friction gets involved, things get hot. If you don't believe me, just rub your hands together real quick. As your hands interact via friction, your hands get hot. So if we take a look at a system that isn't isolated, say here, so here we define, say, this to be my system, and everything outside would be my environment. For my total energy, my total energy could change. And this is because we'll see that there are two ways that we can transfer energy back and forth between the system and the environment. Let me put environment over there, that's better. One way is we can do work on the system, W. Then we will begin to work very shortly. The other, we'll have to wait until we get to the unit on thermodynamics where we can do a heat transfer. Symbol for that is Q. So for the moment, I'll lump these transfers together, and we can say that the change in the energy of the system would be equal to the work done plus the change in other energy, which is basically going to be taking care of our heat transfers looking ahead to the unit on thermo. Okay. So in the next video, we will go ahead and define work, and from that lead up to the work energy theorem.